Hello everyone, good evening. Okay, so welcome to our second lecture, right, on this module. Okay, so I sent an announcement a while ago just to remind everybody in case you missed that in the lecture, that all classes will start at 6:30, all right, and we will have tutorial sessions along the way as and when we cover enough material, all right. So right now we are in the topic of C programming. Once we cover the next topic and we finish up on number systems, then we will have our first tutorial. Okay, so the first tutorial I will upload this weekend. So today probably we'll be finishing up on C programming, and we'll probably do about halfway through the number systems chapter. And once we complete that chapter next week, we should be ready to go ahead with the tutorial. All right. So let me get started. Okay, so last week we started off with this. We were starting off on the review of C programming. All right. So I know most of you have done C programming either in the NUS itself, okay, in your earlier modules, one of your earlier modules, or you've also been doing it in your work. So whatever the case, we will just go through this set of slides as a recap or a revision. Okay. Why we need C programming is we want to be able to because later on when we're talking about the processor and the architecture design, we will be looking at how C code translates into assembly language code, and then from there how the assembly language code is executed by the processor. All right, so that is why we are going in the direction of C. All right, and with C is a lot easier to relate what is happening closer to the hardware. All right, so you will see that when we come to the later topics on processor and architecture design. Okay, so we stopped around this slide here where we're talking about data types, and all the source code that is shown in these slides are also given to you. As what I mentioned, you are free to run it on any platform that you like. It can be a PC-based platform, or you can have or use any of the online compilers like what I showed you last week. Or anything is fine as long as it can compile and execute a C program. Alright, so the whole idea is as long as you get familiarized with some basic C concepts, I think that there's no issue. All right. So in this set of slides where we talked about the size, okay, if you run it, all right, you should generally see something like this. And why I see something like this is because this, the thing that is constant across all compilers is character size. Okay, so character size has always been 1 byte regardless of what kind of system you run on. All right, but in terms of other data types, it could be a difference depending on the actual computing platform you run on, or the processor architecture, or sometimes even the compiler settings and so on. Okay, so there could be other factors that come in to change the way some of this may be interpreted. Okay, but character is always 1 byte. All right, and this is just to give you the idea that different the way we declare variables does matter, because the size of it will determine how efficiently your code might be able to execute on different kind of hardware. All right, so one of the objectives of this module is to appreciate the understanding that though all of you can write very good software and you can get the objective fulfilled, some of these small things like using the correct data type for a particular variable can make a lot of difference, okay, in terms of how fast you can compute. Even writing a loop, later we'll be reviewing loops. Even writing a loop, though we may always generally write a loop going in one direction from 0 all the way to n or n minus 1, in some cases writing it in the reverse way, that means from the highest value down to 0, may translate to better code if your hardware is designed that way. Okay, a processor has certain instructions that interpret it a bit more easier or faster. Okay, so some these kind of small things actually can make a difference in how efficient your code runs on a particular hardware. Okay, so basically a C programming or program structure in C has four main parts. Okay, as what we saw, firstly, we include the header file, all right, depending on what we want. The stdio is a standard IO that we include for the printf and scanf functions. If you have uh, any mathematical related operations, like you want to do a trigonometric operation or so on, then you need to include the math.h. All right, that will have a whole list of math functions available for you to uh, use. You can also define constants, all right, like what we saw here. So those are your preprocessor directives. Then, of course, after that, you have input. Generally, input can be either you asking the user to enter some values or variables, or it can be a file input. You read some data stream from a file that you already have. Then after you get the data in, you do the necessary computation, and then you generate the output. So the output could also be printf or could be a file output. Okay, so this is what we saw just now. The preprocessor directive is basically to include the necessary uh, library functions with what you're doing. So with our stdioh, math or h, if you're dealing with a lot of string related functions, okay, so you have a lot of you're taking in a text file and you want to do some search for a particular text or change lowercase to uppercase, all these kind of things, then you want to include a string.h header file, so that has all the necessary library functions for string related functions. Okay, in terms of using it for the macro, all right, as a constant, the advantage, okay, clearly is that you can always change this constant value in only one location, and automatically it gets updated everywhere you use it in your code. Okay, so that is definitely a big advantage to you. All right, so if after you write your code, you instead of 3 decimal points, you want to change to 5 decimal points or 2 decimal points, you can always just change it in one place and it gets automatically reflected everywhere else. All right, so that is the biggest advantage of using this hex define. All right, and of course, programming, what is it called? Sort of recommended, okay, programming approach would be to use caps, okay, capital letters for the constant. All right, so again, this is a sort of convention that has been always there in place. It doesn't matter if you use small letters, it will still work. All right, basically all it does is it takes whatever string you put here and will replace that string with this value wherever it's using in the code. So if you use small letters pi, it will still work. All right, but the reason why we recommend using caps is because for normal variables, all right, we tend to use lowercase or what we call camel case. In constants, we always use caps. So this is just a programming convention that allows your code to be more readable, only for yourself as well as for others who may do a code review or who may take over your code for future enhancements and so on. Okay, so this is what I said just now. So basically your compiler will automatically replace all the constant values, I mean these definitions, with the actual values that you specify. All right. Input output, again, input is basically to capture your some input from the user through a scanf. So when you use scanf, all right, you are saying that you want to capture some input from the user, and definitely when you want to capture input, you need to prompt the user. So you need to uh, ask the user something or tell the user, okay, give me this particular information. All right, and depending on what information you want to capture, okay, you must set a particular variable, all right, that you or appropriate variable data type to capture this information. So in this case, for example, you're asking for two different information. One is your age, the other is your CAP, your cumulative average point. So your age is, for all of us, we only go by the year, correct? Okay, so nobody says you are 12.8 years old. Okay, so we don't factor in months and try to convert it or anything. So we just look at the years. So that years is always a whole number. So we can define it as age. So we can define it as an integer. All right, or even if you define it as a character is also fine. Okay, basically it's going to be a whole number. For the other one, which is your cap, okay, your cap is basically a cumulative average point. So that is a floating point value, a decimal value, right? It could be 4.11 or something like that. So since the decimal point value, you could use float or you could use double. So in this case, they have used double over here. Now, when you want to capture, all right, when you want to capture the input from the user, use the scanf function. And for the scanf function, there are two parts to it. All right, one is you specify uh, the type of data over here. So percentage D is used for integers, percentage F, okay, so percentage D is for integers, okay, percentage F is for float, and percentage LF is for double. So in this case, you want to capture integer, so use percentage D. You want to capture a double, you use percentage LF. All right, and the other thing is you need to put a ampersand in front of the variable over here when you are doing scanf. All right, when you are doing the printf, okay, so after you do a scanf, you're capturing the value into this variable, and when I want to do a printf, you can directly put the format specifier here, percentage %d, and the variable. So when I want to do a print, there is no ampersand sign, but when I want to capture the data, I use the ampersand sign in front of the variable. Okay, now why do you need to put the ampersand sign? This ampersand sign in front of a variable tells the compiler that I am specifying the address of this variable. All right, so basically what is happening when I create a new variable, okay, when the C compiler runs and he sees this line here, integer h, that means you are telling the compiler you want to create this new variable and call it h. So when you create a new variable, it has to occupy some memory location, correct? Okay, so inside your vast memory that you have, somewhere your compiler will set aside and reserve a space and say, okay, this is h. This is the space I set aside for each. So this space, this memory space or memory location has a particular address. All right, and that address is basically what we call the ampersand of the variable. That means you put the ampersand sign in front of the variable name. That refers to the address of the variable. So in C syntax, when I use scanf, what I'm doing is I'm trying to capture this data that the user is giving me, and I'm going to put it inside the address which references this variable. Okay, so the address of this variable h is the location I'm going to put this information in. Okay, so if you key in your age as 25, then this data 25 will come into this memory location here. Okay, so that is what the ampersand h does. When I do a printf statement, all right, what happens is I take the data that is inside this, that is specified by this variable, which is age, and I print it out here using this format specifier percentage %d. All right, so those are two different things. Okay, printf, you directly can use the variable name. In scanf, you need to put the ampersand sign because you're specifying the address of the memory location to store this information in. In printf, you're taking the variable that is already represented by this, is taking the data that is represented by this variable. Okay, so in the first example here, you have two printf statements and two scanf statements separately. You can also do a single scanf to capture multiple data together. All right, so again, there are two different options here. Okay, so these placeholders that we put here, or format specifiers, basically tell the code what kind of data we are referring to. So is integer means percentage %d, float means percentage %f, double means percentage %lf, and so on. All right, so these are the common format specifiers you can use. Okay, there are also some variations to how you can specify the format specifier in terms of trying to make your output look maybe neat and presentable in a particular way. Okay, so for example, over here, if I specify percentage %5d, then I say I want to represent the integer in width of 5. Okay, then it's justified and so on. So there are a lot of different variations to this. I will not go through all of that. If you're interested, you can just look up, okay, to see how you can print out a particular variable, the data in a variable, right justified or left justified, what is the width, and so on. Similarly, if I have a float, I can also specify the width size plus the number of decimal places. So if I want 3 decimal places, 5 decimal places, and so on. Okay, so there are a lot of different variations to how you can use this. Then there are also some reserved escape sequences that you can use to specify certain formatting that you want to put in place. All right, so if I want to print out a new line /n, tab is /t, and so on. If I want to print out a percentage sign, I actually need to put 2 percentage signs together. Then I print out a single percentage. Okay, why you need to do this? Because the percentage sign is actually reserved or is actually used for the format specifiers. Okay, so you need to put 2 percentages together, then you will display a single percentage sign. All right, so these are some of the things of how C operates. All right, so when you are dealing with C, you just need to be aware of this, the way the syntax is to be used. Okay, so we have looked at preprocessor, we looked at input. Now we're going to look at the compute part. For compute part, basically is what do you want this function to do? All right, so you get some input. Okay, after you get the input, what do you want to do? Okay, so if it's a, let's say it's a calculator, you get the actual data, you get the operation, then you perform the operation and you finally give the result. Okay, so in terms of the function body, you can say that you have 2 parts to it. One is the declaration, where you can put in declare variables that you want, and then you execute the statements are the ones that basically perform the actual processing that you want to do. In C, the starting point is always the main function. So when you first start up, you will start off from main. You can of course create many other functions on your own, depending on how you want to structure your whole code. Okay. So again, for creating variables, there are some rules. For example, it has to, it can contain letters and numbers, but it cannot start with a digit. Okay, this cannot start with a digit. So these are some of the rules. Again, in most cases, compilers will be able to automatically point out if something is wrong. Okay, so you don't need to generally memorize all of this, and after a while you will actually be quite comfortable to know what are these rules. Okay, another thing about C is it is case sensitive. Okay, so okay, it is case sensitive, so count and count here are considered different. All right, because this is lowercase c and it's uppercase C. All right, in terms of coming up with variable names, I think you probably have already heard it many times that you should always have meaningful names. All right, and you want to label the names to make sure they truly represent, okay, what it is used for. All right, so if you're having you need to capture the marks from the user or the grade from the user, label them that is along those lines, so you know why you're using this variable. Okay. Okay. Again, there are a whole list of reserved keywords. Okay. That you cannot use inside your variable names or function names. Okay, so I will not go through all of them. So you can look at the list over here. Okay, so as you can see, reserved keywords refers to things that you need to use as part of your C code structure. Okay, so for example, main function is reserved because that is used by the C compiler as a starting point, okay, for your execution of your program. So you cannot have another main function. Similarly, int, float, double, these are reserved keywords to specify your data type for a variable, so you cannot use them as well. Okay, so you can have a look at the whole list, all right. In case you think that there is going to be some conflict, you just need to think of a different name for your variable or function. Okay, so let's look at some of the computational part of it. So assignment statements basically means something equals to something. All right. So if I say like this, KMS is equals to some computation here. So what I'm basically telling the compiler to do is I want to do this computation, which is taking the value in the variable KMS per mile and taking the variable in miles, and I'm going to do a multiplication sign. I'm going to do a multiplication operation, and that result is going to be stored inside this variable called KMS. Okay, so that is basically what we call the L value. The left hand side of the equal sign is called the L value. So we are taking whatever is on the right, performing the computation and assigning it to the L value. Okay, similar thing over here. Sum equals to sum plus item. So I take whatever is in sum, add it to another variable, and put it back inside sum. So the important thing is whatever that is on the left hand side over here must be assignable. That means it must be some variable or something that you can actually assign a value to. Okay, so if you look at the first operation here, 32 equals to 8 is not a valid uh, C statement because the left hand side is a constant, it's not a variable. So I cannot take a variable and assign it to a constant. A constant is a constant. Okay, similarly over here, a plus b is an expression. Okay, so I cannot assign a value to an expression. I can execute this expression and assign it to a value. All right, so certain things that we may be familiar in normal mathematical syntax may not apply directly to C or even other programming languages. Okay, as with all programming languages, you can always write code in a very abstract way, and it might still work. Okay, and my suggestion is always to not do things like this because as always you may forget what you have done and somebody else may have no idea what you're trying to do. Okay, so always try to make it more readable and easy to follow. Okay, so even though you may take a few more lines of code, if it adds to the readability and understanding of the code, I think it's a lot better. Okay, so in this case, okay, basically what you're trying to do is you're trying to compute 3 plus 6, 9, assign it to C, and then assign it to B, and then assign it to A. Okay, so at the end of this statement, A, B, C all be equals to 9. Okay, so you can also sort of specify it a bit more clearly by using brackets. So brackets help to enforce the order of operation, and at the same time you just break it down to 3 lines. I think it's a lot more easier to see what is happening. All right, so like I said, always please try to make your code more readable, okay, for yourself and for anybody else who's going to look at your code. Okay, so there is also a side effect of assigning. When you assign, it actually returns the value to you as well. Okay, so when you do, for example, a equals to 12, it gives you the value 12 back and you assign it to Z. Very similarly, if I do something like this, what happens is B equals to 10 is the assignment that is done. Okay. Following that, you have the addition of 5, then you assign it back to A. Alright, so there's two things happening here. First, you assign 10 to B, and then you take that value 10 and add it to 5, so you get 15, and then you assign it to A. Alright. So there's also this left associative and right associative. Alright. So in left associative, right associative, again, the idea is certain operations are carried out left to right, some are carried out right to left. Okay. So in left associative, basically, if you look at this operation, what is happening is you are first going to perform 46 divided by 15. All right. So 46 divided by 15 is an integer divided by integer. So this will give you the answer of 3. Okay. So later when we look at data types and so on, you will see that the operation, the result also depends on the way you have put in the variables or you have the data type of the variables, okay, will affect the output. So 46 divided by 15, it will be considered that they are both integer divided by integer. So the answer will be an integer. So it will be, so if you key in your calculator, you get 3 point something, all right, 46 divided by 15, but the answer that you will actually get back is only 3. And then you divide by 2 again, 3 divided by 2 is 1.5, but since it is integer divided by integer, you only get an integer as a result. Okay, so the final answer here is 1. Okay, the modulo or remainder is using percentage. So in this case, 19 percentage 7. All right, so basically the closest number you can get without exceeding 19 is 14. Correct, 7 times 2 is 14. So 19 minus 14, you get 5. So the remainder is 5. And 5 percentage 3 means basically the closest you can get is 1. So basically, so 3 times 1 is 3. So 5 minus 3, you get 2. Okay, so that is basically how you get the final answer of 2 over here. In terms of unary operators, you can go from right to left. So in this case, x equals negative 23 means is basically you are basically assigning negative 23 to x. Similarly here, x p equals to plus 4 times 10, you're taking 4 times 10, and then you are making sure it is a positive sign. All right, so there is a difference between putting the plus after and plus before. Okay, plus equals is a compound operation. Okay, so if I were to say p plus equals 4 times 10, all right, this is basically a compound operator, which basically means p equals to p plus 4 times 10. So this is different from this. Okay, in this, you're just taking the operation of positive 4 times 10, and you are assigning a positive value to it, a positive sign to it, and you're assigning it to a variable p. Whereas if I were to put the plus in front of the equal, it is a compound operator, so it is actually a short form of writing p equals to p plus 4 times 10. All right, so that is again some of the things you need to be careful about. Again, left associative, right associative, and all these rules are very difficult to remember, all right, because there are so many. So the best way is always to enforce the order of operation using your brackets, okay, or parentheses. Because once you use brackets, you are enforcing that you want the operations to be carried out in a particular order, and that helps to take away all this guesswork and confusion. Okay, so if you run this code, you'll be able to see what is happening. Now another thing is also the truncation of results depending on data type. Okay, so just now I said just now that integer divided by integer, for example, here you get an integer, but here if we look at this, 9 times 0.5. So it's half of 9, which is 4.5. Alright, so the answer of 9 times 0.5, the initial answer will be 4.5. But you are now assigning it to a variable n, which is declared as an integer. Okay, integers cannot store decimal points, you can only store whole numbers. So the truncated answer, which is only 4, will be stored inside n. Okay, so that is basically how C works. All right. Again, you need to be mindful of this because if you are dealing or expecting decimal points, you want to use float or double. Okay. Of course, some of you may think, okay, why don't I just declare everything as float or declare everything as double? Then I will always capture any decimal point that comes about. All right. Then that is again the kind of thinking that we should not go in. We should not go in the direction because then you may end up expanding and using all the memory for unnecessary reasons instead of using it for more practical applications. Correct. So you could have used the data, the memory for your data processing and signal and your computation and so on, and free up the memory for the variable. Okay, by using the correct data type. Okay, depending on what is the variable supposed to handle. Okay, so these are the associativity between left and right. And like I said, most of us really may not remember most of this all the time. Okay, so the easiest way is always use the brackets. Okay, so this is another interesting slide to give you a better idea of mixed type arithmetic. All right, so integers are whole numbers, floats and doubles are dealing with decimal points. But in many cases, you may have a case or you may have computations that involve mixing both of these together. So what actually will happen? So let's look at it one by one. In the first case, you have 10 divided by 4. Okay, so it is 10 divided by 4 definitely is not a whole number. Okay, so you get 2.5. Now, how do you deal with it? Because m is declared as an integer, finally you will get assigned to only the whole number gets assigned to m. Okay, so the truncation happens. Float p equals to 10 divided by 4. Now 10 divided by 4 is 2.5, correct? Now, but float p is declared as a float, all right, but still you do not get the answer as 2.5 here. Okay, you get the answer as 2.0. Now why is that so? Because 10 divided by 4 is still considered as integer divided by integer. So when you have an integer divided by integer, mathematically we say it is 2.5, but as far as the computation is concerned, since it is an integer divided by integer, your computation is carried out as an integer division. Okay, so you only get the answer as 2. All right. And if you look here, 10 divided by 4.0, the next one, again you have integer divided by float. So when you have integer divided by float, what happens is you are able to perform an actual division in as a float, but since you are assigning it to an integer over here, again the truncation happens now. So you from 2.5 you get 2. Okay, the time when you get it correct is when your variable is declared as a float and one of your parameters in the division is also a decimal point value. Okay, then your division is carried out as a float based arithmetic division. Okay, and you get the result as decimal value 2.5. Okay, the last one here, negative 10 divided by 4.0. Again, it is similar to what we saw just now, where what you have is integer divided by float, So an integer divided by a float, okay, the answer is float, but because you are assigning it to an integer, your final answer is also truncated. Okay. Okay, so how do we go about this? Okay, how do we go about? So one way is, like I said, you do not want to declare everything as float, all right, because that may suddenly make your memory consumption very high. So one way of doing it is to do what we call casting, okay, which allows you to temporarily change, okay, the status or the representation of a variable for that particular computation alone. Okay, so let's look at this and see what is happening. So over here you have integer, okay, a equals 6 and float ff equals to 15.8. So one integer and one float. Now in my first line here, I have float AA divided by 4. Okay, so 6 divided by 15.8. Oh, sorry, 6 divided by 4. Now when I have 6 divided by 4, what happens? So when I say float AA, what is happening is I am temporarily interpreting the variable AA as a float. Okay, I'm temporarily interpreting AA as a float. So this division now becomes a float divided by integer. So the division automatically becomes treated as a float division. So since the division is done as a float, the answer is also given back as a float. So that means you have your decimal values there. So you have 1.5. All right, so that is how you are able to get this. All right, if I take away the float over here, if I take away this float, okay, this line over here, then it would be interpreted as integer divided by integer. So it will be interpreted as an integer division. Okay, so you would not have gotten the 0.5. Okay, now let's look at the next line and see what is happening. Here I have integer ff divided by AA. Okay, so what is integer ff divided by AA? So integer ff, that means ff is actually a float, 15.8, and then I'm going to take ff and I'm going to cast it as an integer and I divide it by AA. Okay, so since ff is a float, but I casting it as an integer, that means for this operation I discard the decimal values, so I treat it as an integer, which is 15. All right, and I divide it by 6. All right, and I will get 2 point something. Okay, so since it is now treated as integer divided by integer, I only get the integer result. So the value is a integer over here. Okay, and let's look at the last one. In the last one, I have float AA divided by 4. Now, float AA divided by 4, AA is 6 divided by 4, and I'm casting it to float. All right, but if you look at this and this, okay, what is the difference? Okay, why is it in one case I get the 1.5, the other case I only get 1.0? All right, so this is again important. The main difference is in this first line over here, I treat the AA as a float. Okay, and then I do the division. That means as far as the division is concerned, it is a float divided by integer. So I perform a float division over here. But in this line, what is happening is the division is carried out separately, okay, because of the brackets, and then I cast the result to a float. Okay, I cast the result to a float. So when I look at the division separately, what happens is I have integer divided by integer. So this is actually a integer division. So when I have an integer division, 6 divided by 4, I get 1. And since I cast it to a float, then I get 1.0. Okay, so the reason why you don't get the full answer here is because the division is still interpreted as an integer division and the casting is done after that. Okay, so you have to remember that if I want to perform the division as a floating point division, then one of the variables must be a float or must be cast to a float. Then the whole division operation is interpreted as a floating point division. Okay, so that is the difference between the first one and the last one over here. Okay, so now let's look at some other parts of C. One is, of course, control structures to decide which code to execute or which one to skip. All right, so of course, the most common one everywhere, I think almost all programming languages, is if else. So you can have a particular if or multiple or if else or multiple if, else if, and else, and so on. So there are many different ways of structuring it. You can also have switch case statements. In switch case statements, your value that you are comparing to must be discrete values. Okay, so for example, you have a number and you're only checking for the number to be either 5, 10, or 20, and then default is if it doesn't fit anything else. All right, if I want to check for a range of values and so on, definitely the if else is a lot better. Okay, in terms of checking and whether two values, how they are related, okay, you can use the conditional operators here. In this conditional operators, you have to always remember that I think the less than, greater than, and so on, those are well known. What you probably want to take note of is the equal. Okay, so to compare for two numbers to be the same, you can say equal, and for that is actually double equal sign. For them to be not equal, you say the not is the exclamation mark over here. Okay, in C, there are no Boolean type. There is no particular Boolean data type in C. So what we say is anything that is, as long as you see 0, you say is false. Any non-zero value, let me see, anything else, could be positive, could be negative, doesn't matter. Any non-zero value is automatically treated as true. Okay, so only 0 is false. Anything else is considered true. Okay, so if I look at this here, is 2 greater than 3? So 2 is not greater than 3. So when I do this, when I write this expression, the result of this would be either true or false. So since this is false, I get a value of 0 assigned to A. Okay, in the second line, 3 is greater than 2, so this is true, so it is 1. Okay, so even though you don't have any particular separate Boolean type in NCC, you can just assign it to a character variable or integer variable. You can just hold the result of the comparison. In terms of logical operations, okay, you can use and, or, not. Okay, so this is basically your normal, what you call Boolean logic. Okay, so to check whether two conditions are true, okay, we use two ampersand sign, either or. In terms of check, you use two or signs. All right, the not is the exclamation mark. All right, so these are just basically the sort of logical comparators to relate different conditions together. Okay, so again, these are all the precedence and associativity and so on. I will not go through this. You don't need to remember all of this. As long as you specify them in brackets, I think you will automatically know what to do first. Okay, and that should be the preferred practice. Okay, when you're writing your code. Okay, so let's look at this expression. So this is again how you should not write code, because when you look at this line over here, okay, you seriously do not know what to do. How do you interpret it? Okay, you do not want to be looking through the precedence table and figuring out what is actually happening. Okay, uh, so in this case, okay, what would happen is your DCC would issue a warning, all right, because the order of interpretation is left to the order of how it is defined in the precedence table. All right, so the GCC or most compilers will issue you a warning uh, just to make sure that you are aware that something is going on here, and it may not be what you think it is. Correct. So the better way is to do something like this. So if you do something like this with the brackets, then I think you can see a lot clearer what is happening. Okay, so let's look at what is happening here. A greater than B. So you are evaluating this operation and you're doing all with this operation and the end with this operation. So there are three separate operations that you first need to evaluate. All right, and then you can come to the next step. So the first one is A greater than B or B greater than C. So what is A? A is 4. Okay, so let me put the values here. B is -2. Okay, B here is -2 greater than 0. A is 4. Okay, and B is -2. Okay, so if I do it this way, what happens? So A greater than B, 4 greater than -2. Is 4 greater than -2? Yes. So this is a true. Is B greater than C? No. Correct. -2 is not greater than 0. So this is false. And this is an OR operation here. Okay. And I do an AND with 4 equals to -2. So is 4 equals to -2? No. Okay. 4 is not equals to -2. So this is false. Okay. So when I do an AND with a false, I don't need to worry about this because I know that the end result is always going to be a false. So this one will give me the answer as false. Okay, so this is why it is important to understand or the need for putting in brackets, okay, to enforce the order of interpretation. Okay, so you yourself do not get confused with which one is going to be evaluated first. Okay, so let me write this here. So since I covered that, so what is written here is A greater than B and with not of B greater than C. Okay, so A greater than B. So is A greater than B? 4 is greater than -2. So that is true over here. B greater than C. So is B greater than C? No, B is smaller than C, correct? B is not greater than C. So this is actually false, right? This is actually interpreted as false. But I have a not here, correct? So not or false means the inverse of false. So this would be true. So true and true, the answer would be true. Okay, so the final answer here is true. Okay, so if you're not very sure, you can always go back to this. Okay, if you're not sure of the logic. Okay, as far as AND is concerned, AND operation here, as long as only when both of them are true, the output is a true. If any of it is a false, okay, any one of it is a false, the output is going to be a false. For the OR operation, as long as any input is true, okay, the output is going to be a true. And the not operation or the exclamation mark in front, that is basically to invert. So false becomes true, true becomes false. Okay, so these are the basic logic operations that you need to be aware of. Okay, so in terms of the short circuit evaluation, when you're doing an OR operation, as long as one of it is true, automatically you can say the result will always be true. Okay, so because in OR operation, as long as one is true, everything is true. In AND operation, as long as one is false, the entire result is false because you want everything to be true. Okay, so that is a short circuit evaluation that the C compiler might do. Okay, in terms of repetition structures, you have while, do, and for loop. So these are basically three different ways of writing loops to repeatedly do perform some action. So in all cases, you have some initialization, you have some condition, and you have some update. Okay, in while loop and do while loop, you can see that the update and initialization is not shown. Basically, what will happen is the initialization is done prior to the start of the while or do while, and the update is also done. The update is done somewhere inside the loop. Okay, so somewhere either in the beginning or towards the end, you will do the update. Same thing for the do while loop. So it all depends on what you're trying to do. Okay, in for loop, everything is written in the same line in the beginning. Okay, so in this case, you have sum 1 to 10. Okay, so if I were to use it in a for loop over here, I put the starting value for the variables. Then I say what is the condition that I need to fulfill to keep on iterating through the loop again and again. And every time I iterate, what is the change that I go through? Okay, these same three pieces of code are just put in different places for the while loop and the do while loop. For the while loop, I keep on repeating the same thing. This is the condition, and the increment is here. The initialization is done outside the loop. Okay, similarly over here, in the do while loop, I put the exit condition over here, initialization in front, and this is the increment or change in the count. Right. So the only difference between while and do while is in a while loop, you always check for the condition first before you even start executing one iteration of the loop. In a do while loop, you will do at least one time. Correct. So at least one iteration is guaranteed. All right, and then you will check whether to repeat it after that again. Okay, in some cases, you may write a loop, but you may have some condition to exit the loop earlier. All right, so how do you do that? You can use a break statement. So if I look at this piece of code here, I'm having an iteration of 5 times, and each time I print out the number and I print out a ya. So it's 1 ya, 2 ya, and so on. If I were to put in a break statement, okay, so in this case, if I equals to 3, I break. Okay, so when I break, what happens is I will exit and go to the end of the loop and go back to start the next iteration. All right, so in this case, when I equals to 3, when I break the loop, I will come to the end and I will exit the loop, not go back, sorry. Okay, so I'll exit the loop, all right, and carry on with the rest of the program over here. So that is what is happening here. I print out 1 ya, 2 ya, and 3, I don't print the ya, because the moment I equals to 3, I will break out from the loop and I will not go back anymore. I'll carry on to the line of code that is after the loop. All right, so the continuing part happens, okay, when I have what is known as a nested loop. So in a nested loop, I have an outer loop and inner loop, like what is shown here. And when I have a break, okay, in this case, the break is in the inner loop. So when I break in the inner loop, which is here, I will carry on to, so when I break from the inner loop, I will still carry on with the code, which means that I still have the outer loop to carry on to. Correct. So in the outer loop is where the first variable gets incremented. Okay, so I break again and the first variable gets incremented. Okay, so it's the same principle as just now. When I break, I will exit the loop and carry on. But in this case, when I carry on, I'm actually carrying on to the outer loop. So I actually carry on again from the outer loop and then come back in again. Okay, so that is a nested loop. Okay, similarly, instead of breaking, I may choose to skip some part of the code at certain points in the loop. Okay, so the same thing as just now. Okay, And to do this, I use the keyword continue. So when I put the keyword continue instead of break, what happens is I will actually carry on, okay, without executing the rest of the code within that loop. Okay, so when I say continue, whatever is after this continue line, I will skip. Okay, I will skip the rest of the code within the for loop, and I will go back and continue with the next iteration of the loop. Okay, in break, if this instead of continue, I put a break, I will skip everything, go to the end of the for loop, and carry on after the for loop. Okay, so that is the difference between break and continue. Okay, for a nested for loop, okay, when you say continue, basically means the same thing. I will skip whatever is after this line, and then I'll go back. So in this case, for 3 alone, I do not see the printout of the word yeah. Okay, so that is the difference between the continue and the break. Okay, in the break, you will break out of the inner loop, and then you will carry on from where the code is. In continue, you will go to the end of the loop, and then you start the next iteration of the loop. Okay, so break and continue are good ways of running your code in a loop, but at the same time, for certain conditions, you may choose to either temporarily not do or momentarily not do certain things in the loop. Okay, so that basically brings us to the end of this set of slides. Okay, so I know we talked about a lot of things in C programming, and I will say that it is quite a compact crash course, but this is not a C programming module, right? So the reason why we just going through this overview of C programming is just to make sure that you have this basic foundation in case you have lost touch with it, and then you are able to apply it later on. All right, so that is basically the C programming part. Okay, so what we can do now is we can go for a short break, okay, because the next topic is on number system. So let's go for a short break now. Okay, now it's 7:30. Okay, we can go for a short break over 20 minutes, 15 minutes. Okay, and now I'll see you back here, and then we will start on the number systems. Okay, where we will be looking at the basics of number systems and conversions between one form to another form. All right, and maybe we might be able to finish number systems today as well. Okay, so let's see how it goes. Okay, so let's go for a break, and I'll see you back here about 15-20 minutes time. Okay. Okay, so let's carry on with our lecture slides here. Okay, so we're moving on to this lecture number 3. Okay, so in your Luminous ID, I've uploaded this, I think, over the weekend. Also, on Monday, I think I uploaded this yesterday morning. So this is the lecture slide on data representation and number systems. Okay, so we first need to understand the different ways in which numbers can be represented and how we interpret this representation in its different forms. And once we have a better appreciation for this, we can actually move on, or when we go on to the processor architecture part, we will have a much clearer understanding, okay, on how to interpret the numbers that we see there. Okay, so we're going to be covering all of these topics. Some of them will be a bit more detailed compared to rest, but the whole idea is for us to appreciate what is actually happening in terms of the different number systems and how they are used in computing platforms. Now, as what we have seen in the last set of slides, in terms of basic data types, we have character, integer, float, and double. Okay, so of course there are different variations to this, but these are the 4 main basic data types in C. Now, how data is represented basically depends on its type. Okay, and what do I mean by that? If I look at this 8 bits over here in binary notation, 01000110, and I look at this very long binary string here, what does this actually mean? What does it represent? What is the value it represents? Okay, so it depends on what data type we are referring to. Okay, now if I say this first number is integer, then I can interpret it as decimal 70. Okay, so we will come to that in a while. Okay, how to translate this binary into its actual decimal value. If I interpret it as a character, I can say this actually represents character F. Why is it so? Again, we will look at it in a short while. And this long binary bit stream below, what does it actually mean? If I look at it as a integer, I can say that this is actually this huge negative number. And if I look at it as a float number, I can say it is negative 6.5. Okay, so the same ones and zeros grouped together could mean different things depending on what it is actually being used to represent. All right, so that is the whole idea of this set of slides over here. So let's look at the different representations. So in computing systems, basically everything comes down to ones and zeros, basically binary digits, okay, ones and zeros. And these ones and zeros are the ones that would effectively control everything. Okay. Now, in terms of binary bits, we can group them together. Generally, the common terminology for byte is 8 bits. So whenever I group 8 bits together, okay, we say it is 1 byte. Nibble is 4 bits, but it's rarely used nowadays. The next common representation is word, one word. Now, how big is one word is again open to interpretation depending on the computer architecture. Okay, similar to the size of a float or a double. Word also can take on different meanings. So in some cases, you may say it's 2 bytes. Some cases it's 4 bytes. Some cases it might be 8 bytes and so on. Okay, but generally, word is always considered, in most cases, bigger than a byte. Okay, so 1 byte is 8 bits. Then word is usually bigger. Could be 2, could be 4, and so on. N bits can represent 2 to the power n value. So if I say 2 bits, okay, if I say 2 bits, okay, bit 1 and bit 0, so the 2 possible bits, so the different possible combination would be 0 0 0 1 1 0 and 1 1. Okay, so that is basically 2 to the power n. So it is 2 means 2 to the power of 2 equals to 4 different possible combinations. If I have 4 bits, then I have 2 to the power of 4, which is 16. Okay, so in some cases I may have m values to represent in binary, and how many bits do I need? It could be log to the base 2 m. Okay, so for example, if I have 32 different values, and if I do log to the base 2 of 32, I will get 5 bits. Okay, now if I have any number that is not nicely, you don't get a whole number with this, then you take the ceiling. So this symbol that you see here is basically called the symbol function. Okay, so for example, if I have 34 values, okay, so if I say log to the base 2 of 34, okay, you won't get a whole number if you take your calculator. Okay, so I get 5.0, 5.1 something. Okay, so if I take the ceiling, okay, take the ceiling of it, the answer you get is 6. Ceiling means, the ceiling function means you round up to the next integer. Okay, so basically what it tells us is if I have 34 different values to represent, then I need at least 6 bits, okay, to represent these 34 different values. Okay, because 5 bits I can only go up to 32 different values. Okay, so that is basically what the ceiling function is for. Okay, so now let's look back at our positional number system, or what you call the weighted positional number system. Okay, from the time that we started learning maths, okay, from nursery or kindergarten, okay, we are actually dealing with what we call the base 10 number system. Okay, so if I were to give you a number, okay, 154. Okay, right, for this number 154. Okay. Along the way, we learned about ones, we learned about tens, we learned about hundreds. Okay, so we say this is actually 100, 50, and 4. Correct? Ones position, tens position, and hundreds position. Okay. Now, how do we get this interpretation of ones, tens, and hundred? Is because the system that we are dealing with or we have been brought up with is called we call the base 10 system. So actually, rightfully, we must write a small 10 beside each number. Okay, but we don't do it because all of us deal with base 10 systems. Okay, in our normal day-to-day life. All right. So in a base 10 system, basically what we are saying is each number is actually multiplied by a particular weight uh, that is associated with the value 10. So the first weight is always 0. So this number is actually 4 multiplied by 10 to the power of 0. Okay, this number here is 5 multiplied by 10 to the power of 1. And this number here is 1 multiplied by 10 to the power of 2. So the base is 10 and the weighted position is basically this index here. Okay, 0, 1, 2, 3, and so on. Okay, so that is how we actually come up with the ones, tens, hundreds, thousands, and so on. All right. So I mean, when you are nursery and kindergarten, we can't teach you this way. Correct. So we just deal with ones, tens, and hundreds. Right. But now we can relate back and say that the reason why we have this ones, tens, and hundreds is because we have been all the while using this base 10 number system. So every bit, every digit and its position is relative to or is based upon the value is based upon the weighted position of the base 10. Okay, so the 154 is interpreted that way. Okay, so when it comes to decimal points, it's again the same thing. Only thing is you go towards negative power. So if I look at this example, 7594.36. Okay, so 4 is base to the power of 0. This is 1, this is 2, and this is 3. Okay, so ones, tens, hundreds, and thousands. Okay, so that is basically how you get these 4 weighted positions here. Okay, in terms of the decimal point, what you go is you go in the opposite direction. So 3 times 10 to the power minus 1. So this is the first decimal point, this is the second decimal point, and so on. Okay, so it's all based upon the weighted position with the base 10. Okay, so this is of course the general mathematical formula, but as long as you understand how we use this base and the weighted position, then you know how to interpret it. Okay, so of course, base 10 number systems are what we grew up with. All right, we have been taught all our life, so we don't put the base 10 there. Okay, but now in computing, there are a lot of different systems. The two main common systems are what you call the base 2 and base 16. Base 2 means there are only two possible values. Okay, previously we say it's base 10 because there are 10 possible values, 10 symbols, 0 all the way to 9. So these are 10 different symbols, so we say base 10. In a base 2, there are only two possible symbols, 0 and 1. So these are the binary weighted position system. The other one is the hexadecimal system, where you weight in terms of base 16. So base 16 means you have 16 different symbols, and how you represent these 16 different symbols is you go from 0 all the way to 9. After 9 is 10, 11, 12, 13, 14, 15. And these numbers 10 to 15 are represented by alphabets. So you have 10, 11, 12, 13, 14, and 15. So these alphabets represent the values from 10 to 15. Besides base 2 and base 16, you also have base 8. Okay, so again, base 8 is basically from 0 to 7. It is just another system, but it's not so popularly used. In most cases, for most computing systems, you talk about base 2 or base 16. And you can, as long as you understand this idea, you can translate this to any base system. Base 4, base 6. If you come up with your own base system, it doesn't matter, because you now can relate that when I say base 6 or base 9 or base 13, that means I have 9 or 13 different symbols, and then each digit is now going to have a weighted position based on this new base. Okay, so that is the whole idea. In terms of representing these different forms, okay, basically the octal or hexadecimal or binary, in C programming languages, the prefix for hexadecimal is 0x. Okay, so if I were to say integer x equals to 0x32, and if I say integer y is equals to 32, these are two different values. Okay, because 32 without any prefix, okay, by default it is considered a decimal number. Okay, 32. But 0x32 or 0x32 means it's a hexadecimal value 32. Okay, so these are two different values, totally two different values. Okay, so we will see in a while how to relate them together. In the Qt stream, which you will be using later for your assembly language programming, hexadecimal is also prefixed by 0x in front. Okay, in terms of binary representation, you can use different systems in different ways. Some use 8b, some use 0b in front, okay, followed by maybe the decimal values and so on. Okay, so we will need to look at it from the perspective, okay, what is the programming language or the software using, and how that interprets or represents these different numbering systems. Okay, so now let's look at this. So if I look at this example here, I have 1101.101, and I'm told it is base 2. So since it is base 2, basically all I need to do is follow the convention, which is everything has a weighted position, right? So this is 1 times 2 to the power of 0. Okay, and since 0 times anything is always 0, you notice that in my calculation here, I can ignore all the zeros. So I only need to focus on the ones. Okay, all the zeros, and I multiply by 0 is going to give me 0 anyway. Okay, so I can ignore the 0 and focus on the 1. So this is 1 times 2 to the power of 0. This is 1 times 2 to the power of 1, and this is 1 times 2 to the power of 2. And in the other direction, it is 1 times 2 to the power of minus 1, and this is 1 times 2 to the power of minus 3. Okay, so that is how you get your final answer here. So whenever you interpret the weighted position, the final answer is actually your base 10 answer. Okay, your final answer is your base 10 answer. So similarly here, I have a base 8 representation here, and I do the same thing. 8 power 0, 8 power 1, 8 power 2. Okay, for these three numbers. And then the decimal point onwards is minus 1, minus 2, and so on. And the final answer is again in base 10. Okay, this example here, this is a hexadecimal number. So again, the same thinking. You start off with 16 power 0, 16 power 1. Okay, so this is your 16 power 0, 16 power 1, and then this is your 16 power minus 1. Yeah, then you get your final answer here. You suddenly have a different base which you have not seen before. Doesn't matter, it is still the exact same way in which you interpret and get the final answer here. Okay, now let's look at some of these conversions. How do I convert between decimal and binary? Okay, so let me show you the conventional way first, okay, using pen and paper, and then I'll just briefly show you the calculator method. To convert a whole number to its equivalent sort of binary representation, all you need to do is to do a successive division until the quotient is 0. Okay, successive division by 2. Okay, so let me do it step by step over here. So 43, I divided by 2. So I'll get 21. Okay, remainder is 1. Okay, then I do again divided by 2, so I'll get 10 remainder 1. Okay, then I divide by 2 again, I'll get 5 remainder 0. Then divide by 2 again, I will get 2 remainder 1. Okay, then I divide by 2 again, I get 1 remainder 0. And then I divide by 2 again, finally I'll get 0 remainder 1. Okay, so basically what you need to do is to look at the remainders, and the first remainder that you get is your LSB, least significant bit, and this is your MSB, most significant bit. Okay, when you write a binary number, okay, let's say it's an 8-bit number or 16-bit number, doesn't matter. Okay, so the number of bits in between doesn't matter. Okay, the leftmost bit is always called the most significant bit, and the rightmost bit is called the least significant bit. So that's why the answer here is 1 1 0 1 0 1 1. Okay, you start from the most significant bit, go to the least significant bit. Okay, so this is the most significant bit, and this is the least significant bit. Okay, that is how you interpret a whole number to a binary number. Now, how about the fractional part? For fractional part, basically what you need to do is you need to do repeated multiplication until the fractional part becomes 0. Okay. So as you can see here, first step is you multiply by 2, you get 0.625. Then you multiply by 2, you get 1.25. So whenever the first digit becomes a 1, you put that 1 as your carry, and then you remove it for the next calculation. So from here to here, okay, from here to here, you can see that I have removed the 1. So only left is 0.25. Okay, then 0.5. 0.5 times 2 is 1.0. So once the fractional part here becomes 0, okay, until the fractional product here becomes 0, then what will happen is you can stop, okay, the calculation. And then now what you have is you start off with most significant bit and least significant bit. So you get 0.0101. Okay, so if you look at this, whenever you have a number and you want to convert it to its binary equivalent, okay, the integer part you can divide by 2, fractional part you multiply by 2. So you need to do it separately. Okay, you can't do it together, you need it separately. Okay, so let me just quickly show you in your system. Okay, most computing systems you would already have your Windows calculator like this. Okay, and in your Windows calculator, if you select, there is actually a programmer option. Okay, so if you click on that, you can see that automatically I can convert. Okay, so if I go back to this slide here, I just need to key in which format I want, hexadecimal, octal, or binary. So if let's say decimal, I key in for the 3. Okay, the binary value that you see here is 101011, which is here. Okay, the reason why you see the 2 zeros in front is because it always represents the answer in groups of 4 bits or 8 bits. Okay, so since the lower 4 bits and then there's another 2 bits, it automatically puts another 2 zeros in front. Okay, so that is why you see the first 2 zeros. But that does not affect anything because, like what we saw just now, the weighted position only takes significance when you multiply it by a 1. Correct, for binary. When it's multiplied by 0, you still get 0 anyway. Okay, so you can use your calculator. Okay, if you have handheld calculators, all handheld calculators will definitely have, scientific calculators will definitely have some built-in conversion functions already there. Okay, so you just need to figure out how to use these functions in your own calculator. Okay, if not, you just use the laptop. Okay, you can also get this going. Okay, the only thing is it doesn't work for decimal points. I mean, at least not the one on the Windows. But if you have your handheld calculator, some high-end ones might support decimal binary conversion as well. Okay, so that is something you can just try out and see for your own system. Okay, so you can always convert between one form to another form. Okay, easily using the weighted position system to convert it to decimal. Okay, so as we saw just now, you can always convert any number to decimal first. Okay, because automatically when you convert to this one. Okay, so when you automatically apply the weighted position, okay, the answer that you get is in base 10, is the weighted position in base 10. And then from there, you can convert to any other intermediate or any other base as well. All right, so right now we're going to look at some shortcut to convert between base 2, okay, and specifically base 16. All right, so the few example here, one is binary to octal, octal to binary. But like I said, octal is not so widely used, but we will still cover it. Hexadecimal is more widely used and more important for the remaining few chapters, okay, that we will see again and again. Now for binary to octal, okay, we have to group it in groups of 3. Okay, why groups of 3? Okay, because 2 to the power of 3 is equals to 8, and octal is a representation of 8 different symbols. Okay, that means 3 binary bits is enough to represent all the different symbols in a octal form. Okay, so all I need to do is to look at the binary bit pattern that I have and interpret them in groups of 3. Okay, and each group of 3 will then translate to a particular octal representation. Okay, so 001 is 1, 011 is 3, this is 7, okay, this is 5, 6, and this is 2. Okay, if you're not sure how I get these numbers, it's basically, again, you can either use your calculator or you can use the weighted position. So for example here, 011. Okay, so this is again binary representation, correct? Maybe this is base 2. So in order to get to know the value, I take 2 to the power of 0 times 1, that is the first digit here, plus 2 to the power of 1 times 1, that is the second digit here. This third digit here is 0, so I don't need to worry. So this will be 2 plus 1, which is 3. Okay, so that is how you get the answer. If you don't want to do this every time again and again, you just use your calculator. Generally, by the time this module is done, you should become very comfortable with automatically interpreting binary to hexadecimal and decimal and so on. Okay, so if you're seeing it for the first time, it takes a while, but after that it becomes easy. Okay, for the first grouping here, you can see that after I group in groups of 3, it's important that you start from the decimal point and then you go to the left and right. Okay, why is it important? Because then bits that are not represented or you don't have additional bits to represent them, you need to make sure you put a 0 in front automatically. So in this case, since binary to octal, we are grouping in partitioning in groups of 3. This upper 2 bits, you can add one more 0 in front. So that is why you get 0, 1, 0. So 0, 1, 0 is 2. Okay. Again, octal to binary is the reverse. That means take every octal bit and represent it by its 3-bit equivalent. Okay, so 7 is 111. This is 2, 7, 3, 1, 5, 6. So I'm basically taking it in the reverse order, where every octal bit is now represented by a 3-bit binary pattern. Okay, for hexadecimal, it is basically in groups of 4. Okay, and again, why groups of 4? Because 2 to the power of 4 will give me 16, and hexadecimal is a representation of 16 different symbols. So 4 bits is enough to represent all the 16 different symbols that I have in the hexadecimal notation. Okay, so I just need to group them in 4. So this 1 0 1 1, so this will be your B. Okay, this will be your 8. Okay, this is your 9. Okay, this is your D, and this is your 5. Okay, again, all of this you will get to become more familiar once you keep doing or looking at these numbers. Hexadecimal to binary is just the other way around. Okay, that means you take each hexadecimal digit and you represent it in its binary equivalent. Okay, and so on. Okay, so you're going in the reverse order. Okay, and then you get your final representation in binary. Okay, so just now in the first few slides, we talked about this thing called ASCII code. Okay, so what is ASCII code or Unicode? Okay, Unicode is also used, ASCII code is also used, and they are basically ways in which you can represent information. Okay, and it is used extensively for the representation of your keyboard information. All right, so in order to standardize the interpretation of the information sent out when you press your keys on the keyboard, they came up with this code. And basically what this code does is it tells you exactly how to interpret the 7-bit value. Okay, so whenever you press a keyboard button, 7-bit ASCII code is transmitted out. Okay, so that is how your Microsoft Word or your screen or computer is able to interpret this 7-bit code and know exactly what character you type. Okay, so everything is inside the ASCII code over here. Okay, so it's all a matter of interpreting it in a particular way. Okay, so if I wanted to, if I type the capital A on my keyboard, so A is here. So there is 2 pi MSB and LSB. So this is MSB and this is the LSB. Okay, so character A would have been represented by 1 0 0. Okay, 1 0 0 0 0 0 1. Okay, so this is the 7-bit ASCII code that would have been representing the character A or capital A if you were to type it out on your keyboard. Okay, so these are all the other, this is a full table, okay, just for you, for your information only. Okay, so coming back to this slide that we saw earlier, okay, we saw that initially we looked at this 8-bit value and said what could it mean. Now that we have gone through some of these slides, okay, we can see that actually I now can represent this as integer or character. So let's look at it as integer first. Okay, so 0 0 1 0 0 0 1 1 0. Okay, now if I treat this as an integer, okay, treat this as an integer, that means this is base 2. I want to find the equivalent decimal value, means I focus on the bits that have a 1 in it. Okay, again, why 1? Because anything times 0 will still give me 0 anyway. Okay, so let me just write the bit positions here, then it's easy to interpret. So this is 0 1 2 3 4 5 6 7. Okay, so basically all I need to do is to focus on the ones. So it is 2 to the power of 1 times 1 plus 2 to the power of 2 times 1 plus 2 to the power of 6 times 1. Okay, so this is 60. Okay, so let me see. This is 64. Okay, 64 plus 4 is 68 plus 2 is 70. So this will give me 70. All right, so you can see that this bit pattern here 0100 0110. Okay, this is a binary bit stream, so it's base 2. And if I represent this, or if I look at it and I say that this is representing an integer, then it holds the value of 70. But at the same time, I can look at this same 8 bits and say that this 8 bits is actually representing a character, that means an ASCII character. Okay, so if I say that this is representing an ASCII character, what I need to do? I need to now split this into two parts, correct? One is the lower 4 bits, 0, 1, 1, 0, and the upper 3 bits, 1, 0, 0. Okay, because ASCII, you just interpret it as 7 bits. Now I need to look back at my ASCII table. So the upper 3 bits is 100, the lower 3 bits is, lower 4 bits is 0110. So 100 is here and 0110 is here. So the value I'm representing is capital F. Okay, so as you can see right now, the same 8 bits that is stored in a variable or stored in some memory, I can interpret it differently. Correct? So if I interpret it as an integer, I say it is holding a value of 70. If I interpret it as a character, it is holding a value of uppercase F. Okay, now the interesting thing is also that this interpretation of whether it's an integer or character is also about how you write the program to represent it. This 8 bits, okay, this 8 bits here, once you store it in memory, it will always be the same 8 bits. But it is just that you can choose to look at these 8 bits differently at different times also. Okay, so now if I look at this code here, you see that I have two variables, integer and num, correct, 65 and F. Okay, so let's see what gets printed out. In the first two lines over here, I print out num, which is an integer, and I use the percentage %d. When I use percentage %d, I am telling the C program that I want to interpret the values inside this variable as a integer number. Okay, so since the value is 65, it automatically gets printed as 65. Now, if I were to now look at same num, which is the same 8 bits. Okay, so what is the 8 bit? 65. So how do I translate 65 to binary? So let me just automatically use my calculator here. Okay, so 65 in binary is 1000001. Okay, that's binary. Okay, so in terms of binary, this is 1000001. This is the 4 bit and 3 bits. Now, if I look back at my ASCII table, 1000001 is this capital A, correct? It's capital A. So over here, when I take the same 8 bits and I say that I want to interpret it as a character because I'm now using the printout as %C. Okay, so when you use the format specified as %C, you are telling the program that you want to interpret this data as a character, as an ASCII character. So what gets printed out is actually capital A. Okay, so you will understand that the data has not changed. The data is the same. Okay, it is just that the way we are now looking at the data is different. At one time we interpreted it as a number, and in the second case we interpreted it as a character. But it's the same data. Okay, we're just looking at it differently. Similarly over here, CH is a character variable, and initially I assign the value of ASCII-F to it. And ASCII-F is this symbol here. Okay, 0, 1, 0, 0, 0, 1, 1, 0. So this is the representation of ASCII uppercase F. If I were to interpret it as an integer, I use %d. I get 70 printed out. If I interpret it as a character and a printout, I get capital F. Okay, so that is the idea behind the data and the understanding of the fact that we can interpret the way we look at data differently. Okay, so this was one of the, I mean, not past year's exam, but some few semesters back exam, where we had this. Again, this is taken from the full-time students exam question. Okay, not our BTech module. Okay, so in this question, we are basically given this declaration of variable and a for loop, and we're asking what is the output here. So we start off with this number here, 214748364 and then we run a loop for 10 times. So effectively, each time I increment by 1. So since I start off with 40, if I add 10, is the final answer this 50. Okay, so let's keep this first. We will revisit this question later on to understand what is happening. Okay. Now this is the interesting part. Until now, we've been looking at numbers as positive so far, all right, and we looked at decimal parts as well. How about negative numbers? How do we represent and interpret negative numbers in the system? So in order to do that, what we need to do is we need to have a way of representing them. There is some format, some rules on it. So there are 3 different ways or common representations: sine and magnitude, 1's complement and 2's complement. The focus for us will be on 2's complement because that is the default system used in all computing platforms. Okay, your computer, your handphone, and so on. Everybody uses a 2's complement system. Okay, so let's look at the first two first, the sine and magnitude and this 1's complement, and then we will move on to the 2's complement. In sine and magnitude, basically what we say is we set aside or reserve a single bit to represent the sign, and the rest of it is representing the actual value. Okay, so 1 bit is a sign bit, where 0 is positive and 1 is negative. Okay, so in this case, you have an 8-bit value where the upper bit is sign bit and the lower 7 bits are the magnitude bit. So what that means is when I say that I have a 8-bit value represented by this format, okay, I automatically can split it and look at the lower 7 bits separately and the upper bit separately. So when upper bit is 0, that translates to a positive sign, and the lower bits I just normally convert it using my binary to decimal conversion process. Okay, similarly, if my most significant bit is a 1, okay, over here is a 1 actually, then I say that that is a negative sign, and then I look at the rest and I interpret it or the value. So sine and magnitude is quite easy in terms of interpreting it. Okay, you just set aside 1 bit for the sign representation and the other bits represent the value. Now, in sine and magnitude, basically to negate a number, you just invert the sign bit. So there's nothing else you need to do. Okay, so for example, if I say that if you look at this binary bit pattern, okay, 0, 0, 1, 0, 0, 0, 0, 1, and I say this is having a value of 33. If I want negative 33, all I need to do is I invert the sign bit, because this is my sign bit, correct? So the 0 here becomes a 1 and everything else remains the same. Okay, everything else remains the same. Okay, so that is your sine and magnitude. The next one here is the 1's complement. In 1's complement, okay, this is the sort of mathematical representation, but technically it is very easy. All you need to do is automatically you just flip all the bits. Okay, that means the ones become 0, 0 become 1, and that is known as the ones complement. All right, so for example, if I say that I take this number 0000110, if I were to use my calculator and I key in this, I'll get a value of 12. Correct? So maybe let's just see that over here. Okay, so in my binary over here, I just put 1100, I'll get 12. So you don't need to put in the zeros in front, because again, zeros in front, I mean zeros multiplied by anything will always give you 0. So it doesn't matter. I just focus on the first one. It's 1100. In binary, I get a value of 12. Okay. Now this same thing right now, if I were to now say that I want to get negative 12. Okay, so 12 is this. Okay, so 12 is given as 0000110. If I want to represent negative 12 in the ones complement format, all I need to do is invert all the bits. That means 0 become 1, 1 becomes 0. So 1, 1, 1, 1, 0, 0, 1, 1. Okay, now this 1, 1, 1, 1, 0, 0, 1, 1, if I were to key in this in my calculator, okay, let's just see what happens. Okay, so 1, 1, 1, 1, 0, 0, 1, 1. Okay, what I get is I get 2, 4, 3. Okay, I get 243. 1, 1, 1, 0, 0, 1, 1. I get 243, which is also what you are seeing here. So why is this important? Because right now, when I keyed in 1, 1, 1, 1, 0, 0, 1, 1, it is interpreting it as an 8-bit value. Okay, it's interpreting as an 8-bit value. And so this 8-bit value, if I were to just use the weighted positional system, and I ask you to find the value of this 11110011, what would you do? Okay, so imagine that you never see any of these slides, and I just give you this binary bit pattern 11110011, and I say find for me the decimal equivalent of this binary value. Then what you will do, you do the weighted position, correct? You do the weighted position, which is 2 to the power of 0 times 1 to the power of 1, then 2, 3, and then to the power of 4, and so on, correct? And then you add up everything and you will get 243. Okay, but now when I tell you that, okay, now if I give you this information that this 11110011 is actually a ones complement number, is actually a ones complement number, and I ask you for the value, then automatically you will know that this is a number that is in ones complement form. That means it is either a positive or negative number. And how do you know whether it's a positive or negative number? You look at the sign bit. The most significant bit represents the sign. So it's similar to the Sine and Magnitude. 0 is positive. Okay, 0 is positive and 1 is negative. Okay, 0 is positive, 1 is negative. That means when I come back here and now the same 8 bits 1111 0011 and tell you that this is a ones complement number, and ask you what is the actual value. Now you can say that okay, 1111 0011, the most significant bit is a 1, which means that this is a negative number. So in order for me to know the actual value, what I need to do is I need to do the ones complement again, which is 0 0 0 0 1 1 0 0, and that is 12. But because my most significant bit here is a 1 in the original number given to me, that means this is actually a negative number. So I must put a negative sign. Okay, so the interpretation will change, correct? Because now I give you the information that this is actually a ones complement number. Okay, when I don't give you the information, you look at this 11110011, you interpret it as a normal 8-bit binary number, and you can use the weighted position to find out the value. But now when I tell you this information, this is a ones complement number, you can now look at it differently and find the correct value. Okay, so let's look at the next one, and then I'll show you how a calculator does it as well. Okay, so let's look at this. So ones complement, basically all you need to do is, if I want to find the ones complement of a or if I want to represent a negative number in ones complement, all I need to do is to find the binary equivalent of the number in this 8-bit format or how many bits format, and do a complement of all the bits. That will give me the negative representation. So in order for me to represent negative 80, what I need to do is to first find out what is positive 80. Okay, so let's use the calculator here. Okay, so this is positive 80 over here. 0 1 0 1 0 0 0 0. Okay, 0 1 0 1 0 0 0 0. So let me put that here. Okay, so positive 80 is equals to 0 1 0 1 0 0 0 0. So since positive 80 is this, negative 80 is nothing more than the complement of it. So 1 0 1 0 1 1 1 1. So that is your answer. So this is your binary and this is your ones complement. Okay, you just need to take the positive value and perform the complement of it. Okay, the next part here is 2's complement. Now in 2's complement, basically it is exactly the first type is exactly the same as 1's complement. You invert all the bits. Okay, you invert all the bits, but after you invert all the bits, you got one more step. You add 1. You invert all the bits and then you add 1. Okay, so let me come back here. So for 12, okay, so the binary representation of positive 12 is 0 0 0 0 1 1 0 0. Okay, but now I want to do negative 12 in 2's complement. So the first step is I do 1's complement, which is 1 1 1 1 0 0 1 1. Then I add a 1. Okay, that's the second step. I add a 1. So 1 plus 1 is 0 carry 1. 1 plus 1 is 0 carry 1. Then 1 0 1 1 1 1. So 1 more 1 1 0 1 0 0. So your negative 12 is represented as 1 1 1 1 0 1 0 0. This is in your 2's complement. Okay, and this is the important representation. Why it's very important is because, like I said, all computing systems use this representation. Now let's just confirm this in your system. Okay, if you open a calculator and you key in 12 and then you put the plus minus sign, you click on the plus minus sign, you will put a negative in front of the 12. Now if you look at the value, what do you get? You get a lot of ones, all right? But if you look at the last few bits, it is 1 1 1 1 0 1 0 0, which is exactly what we have here. Okay, why do you have all these additional ones in front of this? Is because if your system is a 64-bit system, okay, then it will represent all answers. It will represent this in 64 bits. With a 32-bit system, it will represent the answer in 32 bits. So all the upper bits would become, in this case, 1. Okay, So if I were to remove the negative sign, what does it mean? That means all the upper bits are 0. But since 0, you don't need to write, it makes no difference. Okay. But if the answer is negative, then I need to make sure that the 1 is extended. Okay, so that is why the most significant bit of 1 is extended to fill up all the bits in front. Okay, so this, as you can see, is how your system or your computing platform represents negative numbers using the 2's complement format over here. Okay, so as before, Sine magnitude, 1's complement, 2's complement, the most significant bit already tells us whether it is a positive number or a negative number. Okay, now the same thing over here, 80, and I want to represent it in 2's complement. Okay, so what is 80? Just now we saw okay, positive 80 is 0, 1, 0, 1, 0, 0, 0, 0. Okay, so positive so positive 80 is 0, 1, 0, 1, 0, 0, 0, 0. Negative 80 in 2's complement is first I flip all the bits 1, 0, 1, 0, 1, 1, 1, 1. Then I add a 1. So 1 plus 1 is 0 carry 1, 1 plus 1 is 0 carry 1, 1 is 0 carry 1, 1 plus 1 is 0 carry 1. So it's 1, 1, 0, 1. Okay, so the answer here is 1, 0, 1, 1, 0, 0, 0, 0. Okay, so you can compare this in your calculator just to check. Yeah, so what you get is 10110000. So let's key in that in the calculator. So I key 80, and I key a negative sign here. You can see the last 8 bits is 10110000. Okay, so that is basically how the 2's complement system works. Okay. Okay, so basically you have 3 different systems: sine, magnitude, 1's complement, and 2's complement. All these 3 systems can help us to represent both positive and negative numbers. Okay, and the most popular system is definitely the 2's complement. Okay, and if you can understand that well, then I think you have no problem in interpreting positive or negative numbers when you see them. Okay, so now coming back to this question that we saw earlier. Okay, what is the output? Okay, the output here is not the last 2 digits become from 40 become 50. Okay, and the thing you must understand is when you declare a variable that we saw just now, there is a size associated with it, which is the number of bits associated to or used to represent this number. For integer in Sunfire, okay, so again, why Sunfire? Because our undergrad students used Sunfire, okay, as the operating system to run and compile their C code. All right, so in Sunfire, we have, when you declare integer, okay, it takes up 4 bytes. Okay, so for 4 bytes, okay, you use positive and negative numbers. All right, so okay, maybe before this, I should come back here. And one of the things about positive and negative numbers is the moment you represent positive and negative numbers in a system, what happens is you automatically split the range into 2. Correct? Previously, if I say I have 8 bits, okay, and if I say all the so for 8 bits, what do you have? You have starting from 0, 0, 0, 0. Okay, I think it's, we go with the 4 bits. If I have 4 bits, the smallest number is 0, 0, 0, 0. The highest number is 1, 1, 1, 1. Correct? If you were to key in this in your calculator to find the values or convert it, you basically know that this is from 0 to 15. Okay, and this represents 16 different symbols. Correct, 16 different symbols. Okay, and when I say 0 to 15, that means we are now counting only positive numbers. Correct, 0 to 15. Now I take the same 4 bits and now I tell you that I'm going to represent it as a system that represents both positive and negative values. So now what is going to happen is I'm going to split the range into two. So this entire range 0 to 15 originally is 0 to 15. Okay, now I'm going to cut this in half. Correct, because now the most significant bit is going to represent my plus or minus. So because of that, it is now going to split into two. Now when I split into two, there are different ranges. For sine and magnitude and 1's complement, what you get is, in this case, -7 to +7. Okay, only for the 2's complement form, it starts from -8 to +7. So you get -8 to +7. Okay, so that is why the range here, okay, is given as this: -2 to the power n minus 1 to 2 to the power n minus 1 minus 1. Okay, so for example, if n is equals to 4, that means 4 bits, it is -2 to the power of 3, okay, up to 2 to the power of 3 minus 1. So it's -8 to +7. Okay, so basically this is something is important for you to understand. Why? Because when you declare variables in your C code, okay, if I say integer, okay, by default, any variable you declare is treated to be a signed variable. Okay, a signed variable. That means when you say a variable is signed, okay, so how do you spell it? Is signed is this signed variable. Then you say it is both plus and minus. Okay, that means automatically the range is cut into two to represent negative numbers and positive numbers. Okay, so this 4 bytes of 32 bits basically means that I will actually, since this is declared as integer, so by default it is signed, so I'm actually taking the value range of 2 to the power of 31 to 2 to the power of 31 minus 1. So the largest possible integer is this. Okay, so what will happen in C programming, or generally when in program, when you write a code and you're already at the highest value and you say you want to plus 1 to that. Okay, when you plus 1 to that, okay, coming back here. Okay, so let's say I counting. Okay, similarly when I count 0 to 15, after 15, if I add one more and if I only have 4 bits, what will happen is I will roll over to 0 and start again. Okay, but in a signed number, that means you're positive and negative, when I'm at the highest most positive number and I plus 1 to that, when I roll over, what happens? I will roll over to the smallest negative number. Okay, so when I'm at the topmost, that means the highest positive number, and I add 1 to that, I will actually roll over to the smallest negative number and then start counting upwards from there. Okay, that means if I count, okay, plus 5, plus 6, plus 7, then it will become -8, -7, -6, -5, and so on. Okay, so that is how the system behaves when you overflow, okay, from the maximum value. So over here, what happens is when I'm at the largest value, which is again by 4 bytes, okay, the largest value is this. After I hit 47 at the end, I will actually roll over, okay, to become the smallest negative number, okay, and then increase from there, and so on. So this is how you interpret this answer here. Okay, so you have to understand that when you declare variables, you are declaring them as both positive and negative by default. If you do not want positive and negative, you say that, hey, I don't need to deal with negative numbers in this case. I only want positive numbers only. Then what you can do is, instead of just declare as integer, you can put the keyword unsigned integer. So when I declare a variable as unsigned integer n, for example, then what happens? I'm using the full 32 bits in this case to represent only positive numbers. There will not be any negative numbers. Okay, so that is the difference between normal integer and unsigned integer. Okay, the same thing applies to a character or float or double. So you could have the full range by default split into two. If you do not want that, then you say it is unsigned. Okay, it's all positive. Okay, so in terms of fractions, it's again the same thing. You one's complement or two's complement. One's complement you just invert, two's complement you invert, and then you add one. Okay, so I think we have covered quite a lot of stuff today. All right, so we have a few more slides. Okay, but this one I think we will leave it. Okay, we can carry on in the next lesson. So in these few slides, basically what we have left is the two's complement on addition subtraction. All right, and understanding the concept of overflow. All right, and then the last part is on the floating point number representation. Okay, how do you represent decimal values? Okay, until now what we saw is addition. We saw positive numbers and negative numbers. How about decimal point numbers? How do you represent them in the computing system? So that is the last part. Okay, so the last few parts on addition, subtraction, and decimal point numbers. Okay, so I think we can stop here. Okay, I don't want to overload you too much as well. So next lesson we will finish up this and the last part, and then we can move on to the next topic. Okay, on the processor part already. Okay, so any questions that you all have, you are free to ask. So you can put in the chat. Okay, I can answer for you all. Okay, like I said, don't be too concerned if, let's say, any of the material is tough or difficult. It gets a bit tougher initially, okay, because when once the processor and architecture part comes in, it gets a bit tough and a bit overwhelming, and so that's where you need to sort of keep up and make sure you do some homework, okay, to understand what is happening. But after that, it gets a bit better. Okay, so the first half is a bit heavy, okay, in terms of understanding and making sure you know what is really happening. Okay, so I will be ending here for today. Again, like I said, usually a few days, about 2 to 3 days later, I will just do some simple editing and I'll upload the video for you all to view and revise. Okay. Again, I think about how the class turned up today, which is good. I think the rest probably got tied up somewhere, and no problem. You can always see the video later on. Okay, so that's all I have. Those who have questions, please feel free to ask me. If not, I will see you all next week. Okay, so next week, again, I will update you all with more slides, and I'll also release the tutorial for you all to try first. Okay, some questions you should be able to try, and then we might go through some of the tutorial questions also. I will update you all on the plan next Monday.